Welcome students. Let's start our new chapter for the second unit, and in this chapter we are going to see some more interesting equipments or some more instruments to measure gas velocity using the same resistive type of transducers. So we are looking into the resistive transduction elements, resistance transduction, where the change in resistance is converted to electrical energy, and we have already seen the strain gauge, and we also have seen the RTD, that is the resistance temperature detection. So we have seen about measuring the strain and also the temperature, and today we are going to measure the flow, or mainly we are going to see the gas flow measurement of gas flow using the anemometer, that is the hot wire anemometer, because there are several different kinds of anemometer available in the industry, and that is one is you might have seen there in the rotating in the buildings, that is the vane type of anemometer with some cup-like structures like this. Yeah, might have seen this kind of an instrument. Yeah, that will be, even you can imagine a cock sitting over there. Yeah, like this, a vane type of an anemometer which will be giving you the wind speed. Yeah, so here it is measuring the wind velocity, and hence it is then via an very ancient type of an instrument for measuring the wind speed, and that is also an anemometer. But here we are going to see about the new type of a state-of-the-art instrument, that is a hot wire anemometer, and here this is a resistive element principle. We are going to see the anemometer. There are several different kinds of anemometers, and here we are going to only concentrate on the hot wire anemometer. Let us now start up with why we call it as a hot wire, and also how it is going to work in the principle of a resistive principle, and it's going to get connected with an wind measurement instrument or an anemometer principle. Okay, first we are going to see about, we are going to measure a velocity of gas that is flowing through a pipe. Okay, now you might have studied some things like this in the your fluid mechanics, where you will be measuring or seeing the fluid flow inside a pipe. There we are going to measure what is the flow of this gas. This is the gas flow direction, and here we need to measure this gas flow. What is the velocity of gas flow using the hot wire anemometer? As the name indicates, there is going to be a hot wire placed across the direction of flow. We put it in a new. So this is a hot wire that we are going to place, and it is going to be chambered in between. Usually the wire is made up of platinum and nickel, or nickel, whichever we want we can use it. If you want to have high precision and it should not be burnt, all these things, then you can even go for tungsten, and we can go for nickel. Okay, so these are some different kinds of metals that can be used for hot wire anemometer construction. That is, one is tungsten, platinum and nickel. Okay, so here how it works. Okay, here we have a hot wire which will have a resistance attached to it. Yeah, true, that will have a resistance attached to it. Let's consider it as 100 degrees centigrade. It is maintained. Okay, we are maintaining this wire at 100 degrees centigrade. Okay, you can now even imagine this red pen as a hot wire, and it is having 100 degrees centigrade, and if you are going to blow some air over this like this, when we blow, what will happen? Immediately the cold air from my mouth will hit the hot wire and the temperature will drop. Yeah, true, it's a very simple principle that we are going to hit the hot wire and the temperature is going to drop down. This is the main thing that is going to happen, and this dropping down of temperature will make a change of resistance, as we have already seen in temperature coefficient of resistance. So this change of temperature will change the resistance. Now where you need to connect this hot wire? Of course in the Wheatstone's bridge. This place will be connected to a Wheatstone's bridge. So now I will draw only this hot wire like this. Okay, so this is now is connected over here, and here is our pipe, and this is the flow direction. Okay, and here we have our Wheatstone's bridge connected over here, and this is as our usual the normal Wheatstone bridge which is going to be used. Okay, now so as I told you, when there is going to be no flow change, or that's going to be a constant flow or no flow change, you will first adjust our resistance over here and then bring the galvanometer to a zero deflection, and then when there is going to be a change of gas flow, that will create a change of resistance change, and it will produce the voltage change. That is what going to happen here. Now you very well understand what is the basic principle. That is the temperature coefficient of resistance change. Here we have a hot wire, and then when the gas flow is going to hit the hot wire, this is going to change the temperature, and when there is going to be a change in temperature, the resistance of the wire changes, and we need to capture this resistance change using our Wheatstone's bridge, and from the Wheatstone's bridge we will be able to get the voltage here. Okay, so this is the basic principle, and as I have drawn here, this principle of maintaining here, we are not going to change the temperature, simply we are going to maintain it at a constant current. We are not going to change anything to change the temperature to the wire. We are changing only the maintaining the constant current, and this principle is called as constant current type. Okay, this is a constant current type of an hot wire anemometer, and the resistance will be dependent on like this. When the resistance should be above 2 kilo ohm, we can measure this, and the energy balance equation for this is, these are all you have to remember. Energy balance equation will be I square. As I told you, it is a current type, hence the change of resistance will be equivalent to the I square R, which is the power. Okay, so hence we have I square Rm Ha T of m minus T of R. Okay, and here what are all this indicates are all I is the hot wire current, where Rm is the resistance of the wire, where H is the film coefficient of heat transfer. This is the constant. Okay, and A is the heat transfer area, and Tm is the temperature of flowing fluid, and Tf is the temperature of the Tf is the temperature of flowing fluid, and Tm is the temperature of the wire. You have to change this. Tf is the temperature of flowing fluid, and Tm is the temperature of the wire. And finally, we occur to this relation of this one. Okay, using the current, we will be able to relate it to the flow. Okay, are you very clear with this? This is the first very important type, and it is the hot wire anemometer with a constant current type. Okay, now we will go to the next one. We will go to the next one. Now here there is just going to be a change like this. Simply this is the hot wire temperature type. Okay, this is a constant temperature type. First one we saw about the constant current type, and this is the constant temperature type. Here, as we have seen before, in the constant current type we are maintaining the hot wire at a constant current, but here we are going to maintain the hot wire at a constant temperature by adjusting the resistance here at the circuit. Okay, when we are having adjust the temperature at the constant value at T1 or T2, whatever you can have it over there, then the gas flow over there will try to change the temperature. Again, with the same mechanism of temperature coefficient of resistance, you are going to get a deflection in the galvanometer, and that will give you a output. That output is going to the op amp, and the op amp will amplify the circuit, and you will get an output. Okay, so this is the basic principle over here, and here you have your, this resistance can be taken for your hot wire. Okay, so this is the basic type. You have a hot wire and you are maintaining it at a constant temperature, and the constant temperature will be trying to maintaining it at only at a constant temperature, but the gas flow will try to change the constant temperature, and you will get the output change by the deflection of the galvanometer, which we will capture using the op amp. Next, we have to see the merits and demerits of each, where we have to go in for a constant current type, and what are the merits and demerits of the constant current type and the constant temperature type we have, and what are the merits and demerits over there for the constant temperature type also. Okay, the main thing is here we are maintaining it at a constant current. Okay, so it will be always put up in a heavy load, and there will be a problem of heat because of convention, and you will make the wire to burn as soon as possible, because we don't know the change of flow. If it is going to be very low, then it will make the wire under stress, and it will make the wire to burn out. Then you have to go in for very heavy metals like tungsten and platinum, which will be costly. So this is the main demerit of the constant current type. Convention, this is the main demerit. Okay, the other problem is with the constant temperature type. Okay, in the constant temperature type is we are using an op amp over here, and external circuitry is needed for amplifying the output. Here when you are going for an op amp, then you need all kinds of instabilities and drifts and all these things which we spoke in our unit 1 will come into picture and make the output in an erroneous manner. Okay, so we have to make some noise filtration. Okay, all this kind of electronic circuits will be necessary for the constant temperature type. So this is the main problem with constant temperature type. Depending upon the application, we have to select whether we are going in for a constant current type or a constant temperature type. Please refer your A.K. Shani or else for Krishna Kumar and Kandaswamy book for your this notes. Okay, now we are back. With the piezo resistive effect. The piezo resistive effect, okay, just deals with the same strain gauge principle. Principle of strain gauge. What is the principle of strain gauge that we have seen? Okay, When we are going to apply a force, then there is going to be a change of resistance. Yeah, simply we have a simple beam with a wire connected over here, and when you apply 5 newtons of force, okay, when you imagine this resistance is 5 kilo ohm, when you apply 5 newtons of force, it increases 5.5 kilo ohm. And you remember, I think R is equal to rho L by A. Okay, it's piezo, which is mechanical stress, resistive, which is resistance change, effect. Okay, so the same thing, only it's given as piezo resistive effect, which is the principle of strain gauge. Whenever there is going to be a material or a material is put up under a mechanical stress, it changes its resistance, and this resistance has to be captured, and this effect is called as piezo resistive effect, and it is applied in several applications. As we have seen before, the strain gauge, the strain gauge can be used for measurement of force, pressure, and using strain gauge you can build a load cell. Okay, all these things are possible. So this is the main thing. So maybe I can even say about a load cell. A load cell is simply a pressure transducer or a force transducer. Can you imagine a 5N? It's a cantilever beam first. This is a hollow block inside. You can imagine now this is a cantilever beam. Inside this is a primary transducer. Why it is called as a primary transducer? As I explained before, the entire body of the load cell, only we are giving the force. Inside it has the strain gauge attached at different places depending upon the amount of output that we need. Usually it will have around a full bridge strain gauge. That means 4 bridges will be 4, instead of the 4 arms of the Wheatstone's bridge, it will have 4 strain gauges connected at one side, and also the other side there will have 4 strain gauges connected, and finally the output will be taken and the change of resistance will be converted into voltage using the Wheatstone's bridge. This is the load cell. The load cell can be applied for several different kinds of applications. As you have seen here, we are applying a force, which is the force may be coming from a weight, where the weight can be calibrated to your resistance change. This resistance change which is calibrated, can be used as a weighing balance. Okay, that you might be seeing in the laboratory. So this is a load cell arrangement. So here we have all our resistive effect that is happening here. Finally, we come to our humidity measurements. What is humidity? What is moisture? It is the amount of water vapor that is present in the atmosphere or else in a material is called as humidity or a moisture. Okay, and we have the term absolute humidity, which is present in the moisture that is present in air, is called as absolute humidity present in a material, and relative humidity which is equivalent to the humidity in the material divided by humidity present in air. This is relative humidity. Why it is called as a relative humidity is, we are comparing the humidity present in the air to the material's humidity. That is the reason that it is called as relative humidity. And how we are going to measure this relative humidity using the resistive type of sensor is again a very simple task. You imagine again something like this, a wire which is coated with some hygroscopic, see the term, hygroscopic medium. Hygroscopic medium is coated over totally it is coated over this wire. Okay, this wire, what is hygroscopic? It can absorb moisture. It can absorb moisture. The best example I can say, which you know, is H2SO4. Just take a cotton wig, okay, and then dip it inside concentrated sulfuric acid and you place it in a open atmosphere. It will be diluted. How it gets diluted? Because it absorbs the water vapor around and it becomes diluted. Okay, so this is called as the property of hygroscopic nature. Okay, so like that, we are coating the wire with a hygroscopic material which can absorb moisture from the surrounding environment. Okay, this one which is coated with hygroscopic material is exposed to the environment where you need to measure the moisture, and the moisture gets stuck to all the places by changing its resistance. Before it had a resistance which you have balanced to the Wheatstone's bridge, and after absorbing of resistance, let us take for 10 minutes you are leaving it in a room temperature, in an open room, and you want to find out the humidity present over there in the room, then you will be finding a deflection in the galvanometer depending upon the amount of moisture present in the room, and you will be able to find it. Something like this it is. Again, you have to put up a Wheatstone's bridge. Wherever you go, you can't leave it in the resistive type. And here you have this wire which is coated with, again, a hygroscopic medium. Okay, and this hygroscopic medium will produce a change of resistance. Initially, without exposure to our room moisture, it had a deflection over here, which will be equivalent to 0, and then after exposure to the room moisture, it becomes change of resistance. Then you will be able to get the what is the moisture, which can be calibrated to the voltage over here. So this is the basic principle behind the humidity measurement over in the medium. So thank you very much. So we have even completed the humidity measurement, piezoresistive, and also the hot wire anemometer unit number 2. And our next unit number 3, will start with the inductive type of transducers. Thank you.